good morning. It's the physics video lecture. Physics 105B, video lecture 37. So we're doing Hamiltonian mechanics, and we have the concept of the phase space. So I'm going to review a little bit, and then we'll tackle a really nice example. Okay, so phase space. Phase space. So we have to have a Hamiltonian system. We're looking at one with conserved energy. So we've done all the work it takes. Coordinates, velocities, momenta, Lagrangian. Finally, we have the Hamiltonian. Q1 to Qn, P1 to Pn. And the phase space is the set of it's a two n-dimensional space of these n coordinates, these n momenta. They're all treated as dynamical variables. And with Hamilton's equations, we have, and I'm going to write it as a vector now, Q dot is dH dP, so that's those n derivatives, and P dot minus dH dQ. So that's those n derivatives there, or d dt of this vector QP, of that is equal to dH dP minus dH dQ. And then I showed this is a vector field right here, vector field, and this is a position vector in that 2n dimensional space, all 2n of these. And so that's just the motion of that position vector in 2n dimensional space. I could even write it this way, d dt of x equals f of x. And then I would have to rename these things. So x sub 1 to x sub 2n, that would just be these q's and p's. And this function here, vector function, would just be these things here. So I could relabel it. This form is kind of interesting because we were talking about stability analyses in the sense of a differential equation of that form. And actually we're going to return to that. We're going to make a connection to that again. So those are the different ways of looking at it. And if you want to graph these things, you're either limited to 1 degree of freedom and 2-dimensional phase space, or you can imagine this is n dimensions, that's another n dimensions, okay? You have a point in phase space, and you see now that a point in phase space corresponds to an initial condition, okay? So, because it's initial position and an initial momentum, okay? And then this vector here, we'll go ahead and stick with this system right here. Right. This vector here, this vector field, is what? It's pointing into the direction of this generalized, this velocity of this phase point, okay? And for the harmonic oscillator, we know that this point, its next direction is going to be here. Okay. And in fact, if you are here with the harmonic oscillator, which we're going to return to in a moment, then that's a positive position, okay, positive Q, and a positive momentum, okay. If you're at this point, that means you're at your maximum, okay, you're at the maximum of the position, and therefore your momentum is about to go negative because you're going to head left again. And that's how that circular pattern was derived. So I'm going to do that. I'm going to discuss that again, and then keep going with it. So let's write down what we have for the harmonic oscillator. because we had our Hamiltonian E squared over 2m plus kq squared over 2 equals h, and that's constant, so that's equal to E. And then the derivatives of Hamilton's equations, we explicitly had the vector field for this, and then we could interpret this as an ellipse, and so for a given energy, or I'll write H equals E equals constant, and then we have E squared over 2mE plus Q squared over 2E over K equals 1. And I just did the square root squared because then we have an ellipse and we can mark off its boundaries here. But yeah, so for any given any given energy, we have an ellipse, smaller energy, smaller ellipse, larger energy, larger ellipse. And you can see this point, the stable equilibrium, is surrounded by these concentric circles of clockwise orientation. And any point on this circle is an initial condition to the system, and its vector is tangent to that point, okay? Yeah, okay, so there we go. Now here's what I want to do. I want to extend this system to a physical pendulum that can rotate a full 360 degrees. Okay, so we'll do the physical pendulum. I'll probably start a new board for this. So yeah, the phase space, we've got the phase curves. I mentioned the fact that these do not intersect because of uniqueness. And good, I'll send this up here. So this next example we want to do pretty thoroughly. And maybe I'll leave, maybe I'll leave some steps for you guys to do. We'll see how this goes. So it's the physical pendulum. It's not restricted to small oscillations. And I'm not sure what nomenclature we'll use, but so this example, we want to do this pretty thoroughly. So physical pendulum. And the idea is we could even have a board here or something. There's the axis, and we can just spin this thing around. Okay, it's not just going to be small oscillation, we can give it a full spin. Small oscillations, of course, are part of it. So the Lagrangian, okay, so if we remember how this physical pendulum went, right, we had the mg, and we had a distance d here. So the equation of motion was I theta second derivative is equal to minus mgd sine theta. Well, we want to start with the Lagrangian. Okay, but we remember that was how we constructed the equation of motion. But for the Lagrangian, the kinetic energy will be 1/2 I theta dot squared, and the potential energy will just be negative mgd cos theta, right? We can have a constant in there, but that's just the standard pendulum potential energy if we're at the center of mass there. So if that's our Lagrangian, let's go ahead and get the Hamiltonian. So then we have P sub theta is equal to dl d theta dot is equal to I theta dot. And we know that the energy for this basic kind of Lagrange is just the kinetic plus the potential. So we'll go ahead and write it this way. Not yet the Hamiltonian, but I'm already giving it the letter. Negative mgd cos theta. Okay, now we'll turn it into the Hamiltonian. And it'll be piece of theta squared. We'll do both steps. So 1/2 I theta dot squared is piece of theta squared over I squared negative mgd cos theta. So it works exactly like the mass on the point particle. So no problem there. So what do we have? H equals P, and that's piece of theta. I'll leave it there, piece of theta squared. 2I plus negative mgd cos theta. So we can get Hamilton's equations for this, and we can get the phase space. Yeah, so let's go ahead and we have theta dot is equal to dh d piece of theta, only right there, so it's piece of theta over I. Of course, that's what we had in the first place, but just to write it out. And piece of theta dot is equal to minus partial h partial theta. And that's just going to be, so the cosine of a minus sign, so 3 minus signs. So right, minus mgd sine theta. So those are the equations of motion. Well, we want to do the analysis. And again, if you plug these equations of motion together, then you're back to the original. Now let's go ahead and do that just for completeness. Make a little boundary here. So piece of theta dot is I theta double dot. Okay, so we have theta, the second derivative is equal to minus mgd divided by I sine theta. And this here we can call omega naught squared. That would be the frequency of small oscillations when we do the linearization of the sine. So we'll have that just for completeness. Theta second derivative minus omega naught squared sine theta. Small angle approximation, then linear harmonic oscillator. Okay, no problem. Okay, good. So we have pretty much everything up here. Now we want to construct the phase space and the phase portrait. So let's see. Phase space and phase portrait. So what we have here, we'll do a couple of these. So we have theta and we have piece of theta. That's our Q and P. Let's solve for piece of theta squared up there. So piece of theta squared then we'll take the square root. So we have 2I H, which is a constant now. We could also call it E, H plus mgd cos theta. So when theta is equal to 0, we have H plus mgd, and when theta is equal to pi, we have H minus mgd. Okay. So let's even go ahead and take square root. So we got plus minus square root of this. And so we could use this to graph out the phase portrait. We'll start with small oscillations. Right, and the plus sign would be the upper part of the curve, and the minus sign would be the lower part of the curve. So, begin with theta less than 1, because they're small oscillations. And a corresponding value of H for small oscillation, which is the energy. Let's go ahead and call this the energy here. You know, we have to change this. Won't be much of a change. We're going to put the 1 minus cos theta there. Minus mgd cos theta. That changes nothing because the derivatives get rid of that constant there. Oh, not so fast. mgd 1 minus cos theta. That changes nothing with what we did right here, but that's more useful. So at cos theta, I have to have 1 minus cos theta. Theta minus 1. Okay, there we go. So what about the small oscillations? So theta much less than 1, cos theta minus 1 is equal to 1 minus theta squared over 2. Minus 1, so minus theta squared over 2, and then we go into the piece of theta here, and that's plus minus 2I E minus mgd theta squared over 2. In fact, let's go minus 1/2 mgd theta squared. And we got the square root here. Okay, so this is back to our ellipses. And the piece of theta graphs for these small oscillations with the corresponding energies are going to be just what we had before. There's the equilibrium. So forth. But this is our general expression. And there's our general Hamiltonian up there. And what we want to talk about now is what happens when this thing swings around. Okay. We knew we had an equilibrium point when theta is equal to 0, but we also have an equilibrium point, and we did the stability analysis on that recently, which in fact is going to be what we have here. So when this pendulum is standing on its head, so to speak, and this would be an equilibrium, but of course it's an unstable one, it can swing down. So yeah, this is the phase portrait of the generic stable equilibrium. So let's call this the generic stable equilibrium. And what we want to do is see if we can get the generic unstable equilibrium. Generic stable equilibrium, that's what it looks like. It's a dot surrounded by concentric circles, okay? Okay, so I'm gonna hold on to this Hamiltonian. I'll put it over here a little smaller. Hold on to this h e theta squared 2I plus mgd 1 minus cos theta. That's the exact one. So we want the phase portrait for arbitrary energy. In particular, what does it look like if this thing is just spinning around like a propeller? That has to be a possibility as well. So for that, we'll go right under here. We have to be a little more exact. So this is piece of theta and theta, because there's our stable equilibrium point, theta equals 0. The unstable equilibrium is theta equals pi. Okay, so we're going to go out here to pi, and if this thing can spin around, we're going to make sure we go minus pi to pi here. But if it can spin around, 2 pi, 3 pi, etc. Okay. And we already know that the phase portrait looks like this for small oscillations. So the question is, what does it look like if the thing is just spinning like a propeller? You know, this may be a good place to leave it for you guys to study. So here's a question. What does the vector field look like in a neighborhood of theta equals pi? Vector field in a neighborhood theta equals pi, and theta equals pi, comma, when theta equals pi, comma, at equilibrium. That's very important. At equilibrium. So what is the equilibrium for theta equals pi? Okay, well, we can go back to piece of theta. Piece of theta is equal to plus minus 2I E, and now mgd cosine of pi is -1, so we have a -2. E minus 2 mgd. square root. And of course, at equilibrium, p sub theta is equal to 0. And so that tells us what the energy of the system is. Energy is equal to 2mgd. Of course, that's just the energy between the thing hanging this way and hanging that way. So that makes complete sense. 2mgd. So there's the energy value, or the Hamiltonian value, and then you want to find those vectors. So you're going to find theta dot dh d p sub theta at h equals e equals 2mgd. Theta, yeah, it's not, yeah, at this point, of course, the vector field looks like nothing, okay? So you actually have to be, did I say, in a neighborhood? Yeah, you have to find it in a neighborhood of this, okay? Right here, it is a point, it's like a point there, but just as a neighborhood here with these little vectors, right? Concentric clockwise. Here, you're also going to find something, okay? Question mark is what? Maybe I'll state the answer and then let you guys, do the little bit of analysis that's required. Let's go ahead and do that, because you want to see, we want to talk about how this phase portrait looks. So if the thing is spinning, that means p sub theta is either always positive or negative, okay? And you're going to get something like this. You're going to have minima here, and maximum here, and minimum right there, okay? Maximum, minimum values, so. You're going to get something like this. The reason it's a minimum is because you're at pi, so it's up here. When it swings down, it picks up speed, okay, and then slows down again. But since it's spinning, it never comes to a stop. So this is your phase portrait, right, for that situation. Okay, we'll do this as well. For a certain energy in which it can spin. Okay, so let's write here. Pendulum is spinning. Blue here. Or rotating, as opposed to oscillating. Okay. And down here, you're going to have the same thing with the arrows in the opposite direction. Okay. So let's call this a max. So you're going to have, it's looking like a wave. And the question is what, so yeah, the vector field here is going in this direction here, in this direction there, but what's going on at that point right there, at the equilibrium point? I'm going to give the game away, and let's call this a homework. What you're just going to do is calculate the vector, which is to say, which we've already done, but you want to sketch the vector. So sketch the vector field theta, theta, and this will, so I'm going to write ddt v sub theta, theta v sub theta, theta v sub theta equals P minus dh d theta. So, because you want to do this and get that connection, what happens here, and you can kind of imagine this, these are no longer ellipses, but all the way to an energy that's very close. Oh, I see I didn't make this as symmetric as it ought to be. Okay, all the way to an energy that's very close, you're going to get some kind of oval here. Okay? Even if it's not mathematically an ellipse. So what does it mean when you actually land on here? Okay. Of course, this is a point, so this line where it actually lands on it is not a physical one, but anything smaller or greater is. What you're going to see, though, is in the neighborhood here, you're coming in and leaving, okay? Just like you were here, coming in and leaving, except since it's an equilibrium, you are coming in here and leaving. Okay, that picture's getting pretty bad. Let's clean it up a tad. This is the answer right here. So in the vicinity of this unstable equilibrium, you have a vector field where the arrows come in and go away. Okay, this is your instability. So if you're just in the neighborhood of that, you're leaving. Okay. So that's the difference. Okay, this is as qualitative a difference as you can get. Let's go ahead and draw it one more time. And what you guys want to do is just analyze these equations to generate that picture. Space, portrait. So let's call this here generic stable equilibrium, and that is these that we've now seen a couple times. There's a stable equilibrium point, and the generic unstable equilibrium. And you know, a pendulum standing on its head, that's as generically unstable as anything, okay? So the generically unstable one is that you're at a point and you have a diverging vector field. Okay? So this one was like that, and this one here has vectors coming and going like that. Clearly different than these concentric circles, okay? That's generic stable, that's the generic unstable. And to complete this discussion, that stability analysis you guys did was precisely for this. Okay? That was the stability analysis that we had for the pendulum. What was that for? Yeah, around pi. It was for the simple harmonic motion pendulum, except instead of small oscillations, it was around pi. So compare to stability analysis that we did. So the upshot of all of this is that Hamiltonian mechanics is geometry in phase space. You've got a phase space, the equations of motion are a vector field, and the analysis of that vector field, these comprise the analysis of the vector field, and you could say there are, two crucial kinds of points, stable equilibria and unstable equilibria, and otherwise, the general motion of that rotating thing, right, is just this wavy thing here that corresponds to that. It's just a smooth, integrable motion out in phase space. Okay. So you can say there are three kinds. You've got this phase portrait here, the unstable one, and then just the motion, general motion through phase space, which is the rotation. So yeah, we can actually put 1, 2, and the 0.3 would be with respect to that blue line there. Okay, I think that's a good place to call it. How we doing here? Well, we can add a little more. So I'll just say something about what you want, what we're trying to do here. So we want to get this vector field, which we actually already have, make sure we have a handle on what the energy values are when we're around here, right? The energy is you're going to have slightly greater than 2 mgd. So 2 mgd would be that equilibrium point. So as long as the energy is greater than 2 mgd, okay, then you can see this piece of theta will always retain its plus sign, right? Something greater than 2 mgd minus 2 mgd, it will always retain a positive amount, which is this amount here. It oscillates between the higher and that lower amount there. And then you want to just analyze your Hamilton's equations and make sure you're able to generate this, or this phase portrait here, okay, this vector field. Okay, good. A little more material in Hamiltonian mechanics, but we'll start that next time. Good. See you guys later.